All right, finally we are wrapping up with influence lines. So by the end of this lecture, you should be able to, first of all, explain the difference between an influence line and a shared moment diagram. Draw the influence line for a moving concentrated load. Use the Mueller-Breslau principle to determine the shape of an influence line qualitatively. Interpret them for a moving concentrated load or a moving distributed load, and be able to place a concentrated or distributed load on a beam to determine the maximum effect on some value of interest. So what are influence lines? First of all, I want you to recall what are shear and moment diagrams, right? Shear and moment diagrams describe how a fixed load affects internal stresses along the length of a member or a beam, right? A shear moment diagram tells you how a fixed load affects the internal stresses, the shear and moment, along the length of the beam. If I place a load here, what does that do to the shear and moment along the length of the beam? Which you then use for design to say, okay, here's my maximum moment, it occurs here. Here's my maximum shear, it occurs here, according to a fixed load. So an influence line describes how a moving load forgot the word diagrams. Describe how a moving load affects the internal stresses at a specific point. Right? If I place my load over here, what happens to the shear at this point? If I move the load, what happens to the shear at the same point? This is a fixed load. This is a moving load. And this is internal stresses along the length. And this is internal stresses at a specific point. From the word moving, you probably know, can guess what type of application this has. Influence lines are used a lot in transportation when designing bridges. Something else that could be moving would be like a crane running along a rail in a manufacturing place, stuff like that. So now we're talking about moving loads. Usually we're talking about fixed loads, dead loads, live loads. They're all usually fixed. Now we're talking about a load that's moving. and where do we place it to get the maximum effect so that we can use that for design, right? So there's two methods of determining an influence line. Actually, there's three, but we're going to start with two for determining functions, right? For determining values, there's two, right? There's our tabulated and there's a function. You might be able to figure out which one's what or how you do them. Tabulated is if you move the load along the length of the beam, and you make a table. If I put it here, this is my result. If I put it here, this is my result. If I put it here, this is my result. Whereas a function, you use the location of the load as a variable. So tabulated right, discrete points. Determine the value. A reaction, a shear, a moment. Right, then you get to make a table out of it where you're like, okay, if I put it here, right? If my length of a member, the location is my x variable, and then here's my value of interest, right? This is an example. Let's say I'm interested in shear at point C. I'll calculate the shear at point C. And I'll vary where I put the location, right? X is the location of the load. So the location changes. Where you calculate the shear, it's at a certain point. That doesn't change. At a specific point. Function. Now we just take that table and make it into a function, right? When I'm talking about the value of interest, I keep talking about a certain reaction, a moment at a certain point, shear at a certain point. Right, and that would look like, right, load location as a variable x. That's still, but my shear at C is now a function of x. So they can be kind of confusing compared to shear and moment diagrams. They're not telling you the same things. Shear and moment diagrams have fixed loads and you're looking along the length to find how the shear and moment changes. Influence lines, your loads are moving, but you're looking at a specific point along the beam to find the maximum effect of the location, the maximum effect of that load on a shear or moment at a specific point, or a reaction which is at a specific point. Yes, your supports don't move, right? So let's do an example. This is, if we were in class, I would ask you to break up into groups, and one of you would figure out the tabulated formulas for the vertical reaction at A, the shear at C, or the moment of D, but we're not doing that. So I'd like you to spend a couple minutes and find, here we have a simply supported beam, and we're going to move this load P along the length, right? Going this way. If this is x equals 0 and this is x equals L, at 8th points along the length of the beam. So 1/8 L, 2/8 L, 3/8 L. And find, if I put that P at that location, that load P, what is my vertical reaction at A? If I put that load P at 3/8 L, what is my shear at the point C? If I put it at 3/4 L, what is my moment at point D? So pick a couple of them, fill it out. The ultimate goal is to fill out this table. So I'm going to have 8th points. So x equals 0, 1/8 L, 2/8 L, which is 1/4, 3/8 L, 1/2, 5/8, 3/4, 7/8, and 1 L. I'll do the first one. Well, I'll do the first two because they're pretty easy. And again, this is the location of the load. Not the length. I'm not making a function of a shear and moment along the length. So let's look at 0 and 1/8 L. This one's pretty easy, right? If I put that P at x equals 0, right? This is x equals 0. What is the reaction at A? Well, I can do the sum of the moments about B, right? Because I'm going to have a vertical reaction at B, so I can't just do sum of the forces in the y direction. Sum of the moments about B is 0. The only loads I have are P acting at a distance from B, L, right? This whole distance is L. P times L acting counterclockwise, so that's positive. And then AY acting at a distance L. So my reaction at A is equal to P. So now, my second thing, my shear at C. Oops, my shear at C. I'm going to draw my beam. This is what we did right when we first started doing shear and moments, right? Calculating a point at Alright, this is my vertical reaction at A. Now I'm going to do my shear at C. So my P is still in the same spot. It's at x equals 0. I'm going to have that vertical reaction AY and a shear at point C. That means this distance, right, is L over 3. Okay, well, let's see. I can do the sum of the forces, and the y direction is 0. Downwards, I have P and BC, and upwards, I have AY. So BC is AY minus P. And I just found out earlier, AY is P. So what's my shear? 0. Right, P minus P is 0. Kind of makes sense. If all my reaction, if I have my load right where I have my support, then it's going straight into the support. It's not even, the beam isn't even seeing anything, any internal stresses. Spoiler alert, right? Alright, so that's my shear at C. Now I'm going to do my moment at D. So I'm going to draw my little beam. I'm going to cut it at D, wherever that is up there. My loads acting on it, I have P at the support A, my vertical reaction at AY, and my moment at D, and this length, right, is L over 2. L cubed plus L over 3 plus L over 6 is L over 2. Okay, let's do the same thing. I'm going to take the sum of the moments about D is 0, so I have the moment at D plus P times L over 2, right? P times L over 2. Acting counterclockwise, so it's positive. Acting clockwise, so it's negative. I have, right, AY times L over 2 is 0. So my moment at D is AY minus P times L over 2. Oh, what did I just say? AY is equal to P, so that's 0. Right, that's 0. So my moment is equal to 0. My moment at D is equal to 0. So I can go back up here. Okay, if I put my P, this is right, location of P, of my moving load, if I put it at x equals 0 right at the support A, My vertical reaction at A is P. My shear at C is 0. And my moment at D is 0. Right? That was a pretty simple one. And it probably means you can figure out the answer down at L as well. But let's keep going for the sake of fun. Okay, that was loading 1, x equals 0. Loading 2, right? I put my P at L over 8. So x equals 1/8 L. Again, I have my vertical reaction at A, my vertical reaction at B. So, vertical reaction at A. Let's see, I'm going to take the sum of the moments about B is equal to 0. I have P acting at a distance 7/8 L, right? L minus 1/8, so 7/8 L. And that's acting counterclockwise, so it's positive, and then acting clockwise, so it's negative. I have AY acting at a distance L. All right. So AY is equal to 7/8 P. Now I'm going to look for the shear at C. Gonna draw my little free body diagram here over to C. I've got my vertical reaction at A, my P, and then my shear at C. This is L over 8. This is still L over 3. The distance from A to point C, L over 3. And it looks like a 4. 1/8 L. Right. All right. Sum of the forces in the y direction is 0. I have minus P minus VC plus AY is equal to 0. VC equals AY minus P. And I just figured out AY is equal to 7/8 P. So if I put 7/8 P, 7/8 minus 1, I get VC is equal to negative 1/8 P. Do the same thing for my moment at D. Right. I don't know if that's big enough or not. Kind of stops like there. Okay. I've got my vertical reaction at A, my applied load P that's applied at L over 8. And I have my moment at D, and D is L over 2 from AY. So, sum of my moments at D is 0. I've got my moment at D plus P times L over 2 minus L over 8 minus, right? That's acting clockwise, counterclockwise, so it's positive. Then my moment, AY moment, AY acting at a distance L. So my moment at D is equal to AY times L minus P times 1 over 2 minus 1 over 8. What's that? 3/8. Again, AY is equal to 7/8 P. So MD is equal to 7/8 PL minus 3/8 PL, which gives you L over 2. I did that, yep. AY is acting at distance L over 2. Phew, okay, I was like, wait a second. Okay. 7/16, right? 7/8. Yeah, make sure you get that. AY is acting at a distance L over 2, not L. And so 7 over 8 times 1 over 2 minus 3 over 8. That gives me PL over 16. So I go back and I say, okay, if my P is at 1/8 L, my AY is what, 7/8? Is that what I said? 7/8 P. Looks terrible. 7/8 times P. My shear is -1/8 P, and my moment at D, my shear at C is -1/8 P, and my moment at D is 1/16 PL. And then I go through and I apply those loadings to the 1, 2, 3, 4, 5, 6, 7 other things. I'm going to give you guys a couple moments. Pick out a couple at least to try if you want to try to fill out the entire table. That's fine, but I'm going to give you a couple moments and then I will fill in the table. Okay, it's been about 5 minutes. If you want to pause and do all the rest of them, or you want to go back and check that you can do this, great. I'm going to fill out all of them. You might notice some trends, right? So that is figuring them out using a table. Now, right, and you can do that, and then you can plot them and see from there. What you could also do, we're going to go down to example number 2, is make a function, right? We're going to figure out the same reactions, and now, or shear and moment, and now we're going to make it a function instead of a table. So let's look at AY. Those are my reactions, AY and BY. If I take the sum of the moments about B to 0, acting counterclockwise, I have AY always acting at a distance L, and then I have my load P acting, oh, see, that's negative because it's clockwise. And I have my load P always acting counterclockwise, so it's positive P, but the distance from B is going to change. What's the distance from B? L, the whole length of the beam, minus X. So L minus X. Right? The length of my beam is not changing. I'm not taking a stress or a moment or shear along the length. I'm saying, what happens to my reaction at A if my load moves? So my function, my location X is, my variable X is the location of my load, right? Not the location at which I've cut my beam, not shear moment. So AY is equal to P times L minus X over L. There's my function. Voila! Right, and you can go back to your table. Okay, if X is equal to 0, P times L over L, AY is P. If X is equal to L, L minus L is 0, right? So if my function is over at my reaction B, right? X is equal to L. AY at X equals to 0, which is support A, I get P. Load at support A. AY, my vertical reaction at A, if my X is equal to L, I get L minus L, so 0, load at support B. Makes sense, right? And you can go and verify those other numbers that we calculated, that those match that function. Now let's look at my shear. Well, my shear at C, at a specific point C that is always L over 3 from the support A, I have two scenarios. I have my load P on this segment or my load P off the segment, right? For 0 to L over 3, right? If this is your distance X, or if my load is to the right hand side of C, it's over here somewhere on the rest of that beam. Right here, I can keep that if you want. It's somewhere to the right. I have my reaction at A and my shear at C, and my reaction at A and my shear at C. If I take the top scenario, let's see, sum of the forces in the y direction is 0. Goodness gracious. Right. Sum of my forces in y is equal to 0. My forces are P down, VC down, AY up. So my shear is equal to AY minus P. And on my last slide, you can go back and check. AY is equal to P times L minus X over L. If I substitute in there, my shear at C, if my load is located in the first third of my beam length, is P L minus X over L minus P, which is P L over L minus PX over L minus P. Those are the same. So my shear is equal to minus PX over L. If I look at the second scenario where my load P is somewhere past that point C, do sum of the forces in the y direction is 0. If I only look right at this little segment right here, I have shear acting downwards and AY acting upwards. So my shear is equal to my reaction. P L minus X over L. So I can summarize those. My shear is equal to minus PX over L if my load is in the first third, or P L minus X over L if my load is in the second third. Finally, let's look at that moment at D, that moment halfway there. Again, I have two different scenarios. If my P is somewhere on that little free body diagram, right? So if my P is located within 0 to L over 2, right? If this distance is X, so this distance is L over 2 minus X. Or if my P is somewhere on the second half of that beam, right? If I look at my first scenario, I have my vertical reaction at A and my moment at D. All right, let's take the sum of the moments at D equal to 0. I have my moment at D. I have acting counterclockwise, so it's positive. I have P, and its moment arm is L over 2 minus X, right? L over 2 minus X. And acting clockwise, so it's negative, AY times L over 2. So my moment at D is equal to AY times L over 2 minus PL over 2 plus PX. I just multiplied that out, right? And I recall my AY is P L minus X over L. I figured that out. So let's see. My moment at D is P times L over L. That's the first, right? Times L over 2 minus P times X over L times L over 2 minus PL over 2 plus PX, P times X. Well, that goes away. Oh, look, I have a PL over 2. I have a PL over 2 minus a PL over 2. Okay? my moment at D, that goes away, is px times -1/2 plus 1. My moment at D for the first half is px over 2. So if my load is anywhere on that first half, I can calculate that moment at D, which is the moment at the center of the beam, by multiplying the location of the load times the load over 2. If I look at my second one, now the load is somewhere out in space. No, it's somewhere on the second half of the beam. So the only forces I have acting are my vertical load and my moment at D. So if I take the sum of the moments about D is equal to 0, I have my moment at D minus AY times L over 2. I figured out what AY is equal to, even though I'm blocking it for a sec. There we go. Right? AY is P times L minus X over L. So the moment at D is equal to AY times L over 2 is equal to P L minus X over L times L over 2. That goes away. That goes away. My moment at D is P over 2 L minus X. If I want to sum it up, px over 2 for x is equal to L over 2. And again, that is the location of my load. That is not my... I'm always looking for the moment at D, which is the moment at the center. And if it's on the second half, P over 2 L minus X. And again, if you took this equation and matched it up with that table, you should get the same values for those discrete points. Okay, now that I have determined my functions for my different values of interest, which I was looking at the reaction at point A, right? Reaction at A. I was looking at the shear at C, right? And the moment at D. Now that I have those functions, I can plot them. And they look something like this. Right? If this is P, and it decreases linearly. Right, like that. Right? That goes along with what I figured out from my tab, my table. Right? Starts at P, decreases down to 0. That means if I put my load right at A, then my reaction at A is P. If I put my load right at the middle, my reaction is P over 2. If I put my load here somewhere, right? I think that's, let's see, this is like, what is that, 3/8, right? And it's like 5/8 or something like that. So this x-axis, remember, is location of my moving load P. Right? My y-axis right here is AY as a function of the location of that concentrated load P. Now if I go to look at my shear, I want to draw that. The shear looks kind of funny. Remember, it had 2 parts to it. It was negative up until L over 3, and then it was going to be positive. If I type those values into my calculator. So I start out at 0, decrease down to, at L over 3, right before C, I would get P times L over 3 divided by L, so minus P over 3. So C happens right about here. Let's say this is minus P over 3. And that's a linear function if you go back and look at it. So it's just a straight line. Then if I look at that function again, and if I put, right, P at x equals L over 3, if I go to that first one, right, so just before L over 3, I get minus P over 3. If I look at the second function, L over 3, I get L minus L over 3, so 2/3 L. So 2/3 P. So let's see, that's 1/3, that's 2/3. So I'm going to jump up. Right, this is 2/3 P. If I go back and look, P at x equals L, not P, sorry, this is V of C. V at point C at x equals L, L minus L is 0, I get 0. It's a linear function, so I know that it's going down to 0. It looks like that, right? So now I know that if I place my load, if I place my P, my moving load somewhere over here on the beam, it's going to result, right? It's going to result in a negative shear at C. If I put it on the second 2/3, I'm going to get a positive shear. My maximum positive shear is 2/3 P, which is just after C. So if I put my load just to the right of point C, I get 2/3 of that applied load, and it is my shear at C. If I put my load just to the left of point C, I get my maximum negative, right? P/3. Still, right, x-axis is location of P. And this, the y-axis is VC of, it's my function of that shear at C, right? At point C. That C point never moves. It's always at L/3. I'm going to hammer that into you, right? Finally, my moment at D, this one's pretty good because, let's look. My moment at D at x equals 0 is 0. If I use that first function, my moment at D, x equals L/2, is PL/4. My moment at D for x equals L/2 for the bottom one, L minus L/2, that's still L/2, so PL/4. And my moment at D at x equals L, L minus L is 0, so 0. And you can kind of guess from looking at that table way back. Right, this is equal to this, right, this is equal to this, this is equal to this, this is equal to this, there's my apex right in the middle. So I draw those two functions. Right at the middle, I have PL/4, I don't know, PL/4. At the ends, I have 0. Alright, let's pretend that goes to 0. So if I wanted to place my concentrated load for maximum positive bending moment, I would place it at the middle. Makes sense, right? Anywhere not in the middle, you're not going to get the maximum bending moment at the center. Doesn't mean you're not going to get the maximum bending moment, but it's not going to be at the center. Just going to write this a third time. The x-axis isn't changing, but this is my moment at D at a specific point, and it's my function moment D of x. So again, this is, if I put, the x is where I put my moment, my concentrated force, and the y-axis is the effect of that location at that specific thing that I'm looking at, right? Right. Sorry, the effect of the location of my force on a specific thing that I'm looking at. If I'm looking at the shear at a specific point, it's not going to give me the effect of that force at any shear along the length. It's just a shear at a specific point. Yeah. Sorry, I lost my train of thought in the middle of that sentence, so I hope that makes sense. So that is what an influence line, how to construct it, using tabulated values and a function. or a function.